work was done in collaboration with Mark Wilder. Actually, while he was still at LSU, I visited him in Louisiana, but now he's in Cornell. And I also, okay, so, right. So first of all, a bit of motivation from physics, maybe even though it's not so, maybe, I don't know. Okay, so like, if we do quantum communication, most of the times we are doing it on optical fibers, right? So that means that there's light traveling through a kind of a medium, so fiber, and you know, light is light, so it can travel through different paths in this kind of glass fiber, and so that means that the field will accumulate different phases. Okay, and so the natural channel that comes out of this process is a dephasing channel. Okay, so something that with some probability distribution P of phi, it kind of applies a phase, you know, to your single bosonic mode. Okay, and the phase is given by the Hamiltonian, which is just the number Hamiltonian. Okay. Okay, so and of course this channel is parameterized by this whole probability distribution, let's say on the whole circle. Okay, good. Okay, this is not a Gaussian channel. That's the first observation. It's just a convex combination of Gaussian channels. So this maybe it's kind of Gaussian channels are kind of the simplest, and this is one step above if you want. Of course, there's a natural example of this, which is when you take a wrapped normal distribution. Okay, so basically you wrap a Gaussian distribution around the circle, so you get it many times. Somehow you get the tail many times. But it's basically a Gaussian. Okay, so with a single parameter gamma, the variance. And this example is important because it was studied before. It comes from a fairly natural process that you can think of. So this was proposed before. Okay, so just to set the stage kind of mathematically, so you have, of course, your separable Hilbert space with the Fock basis, 0, 1, 2, and so on. You have the photon number Hamiltonian. Okay, and it will be useful to think of your density operator as an infinite matrix. And now, by looking at the matrix, we can tell what the action of the channel is. This dephasing channel. And if you input the ket bra and the Fock states ket bra and m, pointed doesn't matter. Ket bra and m, and you apply the channel, you will see immediately that basically since n and m are both eigenvectors of the number operator, you get basically the Fourier transform of the probability distribution P. Okay, fairly simple. So this is that's why it's a dephasing channel, because every off-diagonal element picks up a phase. Okay, and in fact, you can write this as a Hadamard channel. So entry-wise multiplication or Hadamard multiplication or Shor multiplication, whatever you want to call it, of your input density matrix by something which is just depends on P, and it's the matrix of Fourier transform. Good. So it's a very important observation is that this TP matrix is a Toeplitz matrix. Okay. Otto Toeplitz studied this matrices first, partly. Actually, it's not very clear. Yeah. So basically, the entry. So this means that the entry NM just depends on the difference n minus m. Okay. So basically, the whole diagonal is 1. Okay. Because it's a probability distribution, and then all of the entries from the diagonal above the main diagonal are equal. And so on and so forth. Okay, good. And for the wrapped normal distribution, you can do this explicitly. Okay, the Fourier transform of a Gaussian is pretty simple, so you get another Gaussian with a flipped direct. Okay. Good. So basically, this kind of the off-diagonal elements pick up a Gaussian factor that kind of damps the element very far away from the main diagonal. Okay, so this looks like a fairly simple channel. So what do we want to do with this channel? Well, of course, as usual, we want to do many things. So like, for example, want to send qubits. So this is a scheme for quantum capacity. Right, this is a standard drawing. So you want to use the channel many times. So let's say n times to send as many qubits as possible. And the rate by which you send qubits, which is given by basically the log dimension of the system M divided by the number of channel uses. That's your rate of quantum communication, and you want to maximize this rate. Maximizing this achievable rates achievable means that the error that you have at the output goes to 0 from decoding. And so the supremum of all achievable rates is called the quantum capacity. This is a very important quantity. I don't think I have to convince you. And we want to compute it for this channel. Okay. Another thing that we want to compute is, okay, the capacity for generating entanglement. So for establishing long distance entanglement. Okay, this is something that people who do quantum communication want to do all the time. You have an optical fiber or an optical link, and you want to establish entanglement between the two stations. Okay, so then the scheme looks a bit different. You can use the channel, let's say, n times, and in between you can do LOCC rounds. Okay, so local operations and classical communication. So Alice and Bob can talk on the phone and agree on what to do, what measurements to do, what to do depending on the outcomes. And at the output, you want to generate as many E bits as possible. Okay, so a large maximum entangled state with very good approximation. And the capacity for doing this will be in general higher because you allow also back and forth classical communication. And this is called a two-way quantum capacity. And there's also the private capacity, of course, for transmitting secret bits. The two-way private capacity for, well, the capacity for generating a secret key, shared key. And of course, also all the strong converse exponents, which I haven't even defined, but basically, instead of requiring that the error goes to 0, you just require that it stays, below 1, below something below 1. Okay, so you get another 4 numbers. You get 4 numbers for quantum, two-way quantum, private, two-way private, and another 4 for the strong converses, which are in general larger. Well, yeah, never smaller, let's say. Okay, so and in fact, this problem of computing the capacity, this was posed long ago by, well, 10 years ago, well, 13 years ago, by this Jiang and Chen in this paper, 2010. Okay, so, and of course, the main result is that you can compute this capacities, and the good news is that they're all equal. And this comes at a small price of imposing a mild regularity condition on the probability distribution, which cannot be kind of too crazy. It cannot be too peaked in particular. For example, if it's a Dirac delta, then the channel is the identity, so then all capacities diverge. But if the probability has, let's say, finite Renyi entropies for some alpha larger than 1, for 0 larger than 1, then you can compute all of the capacities, and they're basically equal to log 2 pi minus the differential entropy of the probability distribution. So in particular, since all capacities are equal, this means that unlimited classical communication doesn't help you to achieve to enhance the capacity, and also that generating entanglement is exactly as difficult as generating a secret key, which is something we don't expect in general. And if you want a kind of nicer information theoretic depiction of what's going on here, why this formula? Well, this is just the relative entropy between the probability distribution P and the uniform probability distribution over the circle. Okay, so it's a very simple formula. Okay. And of course, and there is also a generalization to the multimode case. This is pretty straightforward from the proof. I mean, not a priori. But basically, you get the same formula. You get the relative entropy between P and the uniform distribution this time of a Cartesian product of the circles. So you get this formula, which is basically the same as before with some n prefactor, and again you have the same regularity assumption. Okay, so so for finite dimensional dephasing channels, this was already known. This was worked out in this paper, a blob paper, as they say. They wanted to be called it. It's in 2017. So what we do is we kind of develop the methods for infinite dimension, which are a bit different, quite different. So in fact, I mean, this was the reason why the problem wasn't solved, I guess, directly in that paper. Okay, so this is basically, for example, this is the plot that you get for the RAP normal. Of course, the capacity will decrease with gamma, because the higher gamma, the noisier the channel. And well, so for gammas, kind of for small gamma, you get this log 1 over gamma dependence. And for large gamma, you get an exponential basically tail, right? So the capacity decreases exponentially. This was also proved in the original paper by Mancini et al. Okay, so plenty of time. So some proof ideas. Hopefully. Okay, so let's say that you have let's say that we try to prove just this two equalities. Okay, let's forget about the private and everything. Let's just prove that the quantum is equal to the two-way quantum capacity and is equal to this simple formula. Okay, so the quantum capacity is always upper bounded by the two-way quantum. So the only thing we have to do is we have to lower bound the quantum and to upper bound the two-way quantum. And that's it. Okay, let's start from the first bound. Okay, so the first bound is very simple because we know actually that the channel is degradable. So well, in general, you know how to lower bound the quantum capacity with the coherent information, which is just the LSD theorem, right? So the coherent information is this quantity defined in terms of the channel. You basically take a bipartite state and you send one half of it through the channel and you compute the coherent information, which is just minus the conditional entropy given by this combination of entropies, basically. Okay, so in general, you have this lower bound. This is well known now, but it turns out that for this particular channel, we know that there is equality because the channel is degradable. Okay, so so it's just a matter of computing the coherent information, in fact. Good. So how to compute the coherent information or to lower bound the coherent information? Well, you input the simplest state that you could input, which is maximum entangled state. Let's say that you do, since we are in infinite dimension, we have to make a cutoff, say from dimension 1 to dimension d, and you send the state through the channel. So what you get is this kind of entropic. So if you compute the coherent information, you get this kind of entropic looking quantity that depends on the like this. That depends on this by the truncation of the matrix TP with the Fourier transform of P that I wrote before. Okay, this was the matrix TP. It's that D by D truncation, and you have to compute basically this kind of entropic quantity. Okay, so you see that we would want to compute the eigenvalues of this matrix. There's a Toeplitz matrix. You can ask yourself, okay, this has a lot of structure. Can you compute the eigenvalues of this? Okay, so for example, this is a 3 by 3 Toeplitz matrix. So you can compute the eigenvalues of this one, but I don't know of a very simple formula for the generic case. So for the D by D case, in general, Toeplitz matrices are not very easy to diagonalize. As far as I know, that's not very nice. But there is one case where they're very simple to diagonalize, which is when they're circular. Okay, so when they actually commute with which means that C is equal to B in this case. So they actually commute with the shift. Because in this case, it's a piece of cake to diagonalize them, because I know how to diagonalize this one. It's just the Fourier basis, and this must be diagonal in the same basis. Okay, so discrete Fourier transform does the job. So now the problem is, when is this matrix, which is Toeplitz a priori, when is it circulant? Well, so if you work this out, you see immediately that this is true if this equality is always true. Yeah, so this equality encodes this equality between entries of the matrix. Okay, so circulant means that so if you work this out, so the matrix is circulant exactly when P is supported on the d roots of unity. Okay, so which is not very surprising, maybe. But remember that we are in infinite dimension, so we can take d to infinity. So then you should expect that so if this is the case, so then this matrix is circulant, and you can compute the eigenvalues. These are exactly d times the values of the probability distribution at your roots of unity.
Sorry, but you said it is important to truncate, so you want to truncate to some finite d.
Yeah, I'm doing everything finite dimensional now, and then I will take d to infinity. That's the only way I know of doing this. Yeah. So exactly working with this truncation, that's of course the heart of the only difficult thing, basically. Okay, so what I'm claiming here is that if P is particularly nice for us, meaning that it has support only on the roots of unity, on the d roots of unity, then the matrix that you get is not only turplets but also circulant. So you can diagonalize it like this in discrete Fourier basis. Okay, but the point is that this will not be true for a generic probability distribution unless you take d to infinity. If you take d to infinity, then kind of the set of roots of unity becomes, in a sense, the whole circle. So you can hope that something nice happens. So if this is the case, you see that you get exactly the formula that I was kind of that I claimed before. So if these are the eigenvalues, then if you work out this entropic expression, you get exactly this. So the point is how to find this for a generic probability distribution P. Okay. So when d goes to infinity, the set of roots of unity becomes dense in the circle, and we hope that this will kind of get us every probability distribution. So the way to do this, rigorously, is to use a beautiful theorem proved long ago by Seger, 1920. So this has been generalized like a zillion times. So the particular version that we use with this very weak regularity condition is due to Serra Capizano, 2002. And so basically what this theorem tells you is that if you look at this matrix TPD and you compute any function of the matrix, so any function of the eigenvalues, and take the trace. Okay, so this is kind of a function of the spectrum of this matrix, and you renormalize by d and you take the limit, then this is the same as computing the function directly on d. So somehow the spectrum of this matrix is really represented by the probability distribution, okay, in the limit. And this works provided that f has this this property. Okay, so this is somehow critical tool. And what does it imply? Well, it implies exactly our formula, because then since this this f, see if you take f to be x log x, you can apply the theorem straight away and you get precisely this formula. Okay, so easy peasy somehow. If you use the Seger theorem, it's kind of the right tool to basically to take care of the truncation. Okay. Good.
You just throw away the circulant property.
Yeah.
These are just the truncations of the Toeplitz matrix.
No, the circulant was just a piece of motivation.
Yeah, it's just a piece of motivation. Yeah, exactly.
You could have used it also, like you could also gone through that, I guess. You could discretize your probability distribution. I mean, that approximates the channel. And then you have to prove a limit of entropies.
Yeah, but if you discretize, then you have to choose a D, and then if you take the
for each D, you have to choose a different one.
Yeah, probably you could.
I mean, what matters for you is that the channel it gives you a kind of an approximating channel, like kind of NPD.
Yeah, somehow
You
yes.
have to prove that those converge.
Yeah, something like this. Yeah, I mean
you could also have done it by hand.
But somehow the circulant argument or the circulant motivation tells you why you should take the relative entropy with respect to the equidistribution.
Right. Yeah,
Sure.
I think you can also do similar things by realizing that Z is the limit of these cyclic, and for cyclic groups, the result is null, right? So then you can just pass to the limit.
Yes, but
Yeah, and on an ultra filter, you need. That's how I can.
somehow you have to.
I can do it without sweat, but.
Yeah, you have to make sure that the capacities are continuous and
there
with a bit slippery.
lots of examples of symbols for which the truncated eigenvalues don't converge to the eigenvalues for.
Yeah, but it's a group thing, right? So I mean, it works for all cyclic groups and actually works for
What
all
works?
compact groups. The
What?
formula, the equality there. For these cyclic groups that was known before.
Yeah, sure. I mean the quality there. That's so.
Yeah,
But
anyway.
so if you want to start with the capacity, how do you start?
I first prove it for cyclic groups. And then I take.
Yeah,
those.
okay, that was known before. For finite dimensional cyclic group, that
Yeah.
was known.
And then you use the fact that the toplets, then you use the fact that the toplets matrices are the limit of the cyclic groups. And the
Yeah,
infinite
but
trace
we
there.
have this entropic quantities, and if you want to take the limits of those, I mean, yeah, it might work out.
They're semi-continuous, so that I think there is a proof, but
It could very well be, I mean, but this is a very simple proof already. I mean, it's not
Yeah.
very complicated. I mean, the lower bound especially, lower bound is fairly
yeah,
straightforward.
it's not the problem.
The upper bound, I mean, one of the two I think will give you trouble because you also need an upper bound. But okay,
Yeah, for compact groups, it's not so.
yeah, possibly. I mean, I can totally believe it, but
Anyway, let's do something more interesting. The upper bound is much more.
the upper bound. Okay, so the upper bound is on the two-way capacity. Yeah, no, the upper bound is definitely there, kind of there. Also because there is, I mean, there in general, there is no general strategy. I mean, for the lower bound, it's degradable, so we know already a single letter formula. So it's kind of okay, just a matter of computing it. But for the upper bound in general, yeah, we are a bit lost. In fact, we don't even have a regularized formula for the upper bound. It's very bad. So the two-way capacity is okay because you have to. So two-way capacity is even worse because you have to optimize over this whole sequence of LOCC maps, and LOCC maps are already very nasty set. So and then you have a whole sequence of those. So, but luckily enough for this channel, it's actually much simpler than it looks because the channel is approximately, or well, in the limit teleportation simulable, meaning that you can always simulate it from its choice state using an LOCC. So in other words, the channel is a dynamical quantity, but it turns out that it can always be simulated by static quantity. So suppose that you tell me, okay, suppose that I tell you, tomorrow I'm gonna give you a state, and I want you to simulate to apply the channel to it. But suppose that you are forced to that your channel expires today. So you have to use it today. So, and what this teleportation simulability tells you is that you can send 1/2 of the maximally entangled state through the channel, use the channel today, and then you will keep the state. And then tomorrow, when I give you the state that I want you to simulate the action of the channel on, you can do teleportation using that entangled state as a resource, and that will simulate the channel. Okay, well, it's a way to bypass the expiration days of the channel. So, okay, so in this case, you know that you can, instead of having this complicated scheme, you can have a scheme that uses, instead of the channel, n times n is the number of uses of the channel, n times its choice state or its truncated choice state. And that will be as good as n uses of the original channel. Okay, and this again works in the limit when d goes to infinity in a strong sense. Okay.
Can you remind us how you check whether the channel is teleportation simulable or not?
Yeah, in general, there is no check, but there is a very simple sufficient condition, which is when it's covariant under the set of unitaries that appear in a teleportation protocol, So for discrete variable, this would be the Heisenberg Weil group. For continuous variable, this would be the displacement operator.
Is it only sufficient? It's not necessary.
Not that I know, no, I don't think it's necessary. So in this case, this channel, although it's a continuous variable channel, it's not covariant under displacement operations, but it's covariant under kind of Heisenberg Weil operations once you fix D. So that's why, I mean, taking care of again, you have to take care of the truncation, but this is also pretty simple. Okay, so then with the teleportation simulability, you can say that a use of the channel is equivalent to the use of its choice state. So I can, instead of distilling entanglement from the channel, I can distill entanglement from its choice state. And I can take the limit of the distillable entanglement of the choice state. Okay, so that's an upper bound. Very good. So now I can use all sorts of tools to upper bound the distillable entanglement of what is a finite dimensional state. Fantastic. So you just need to choose one. So the classic one is the relative entropy. So let's say you do the relative entropy of entanglement of a finite state, which is even a maximally correlated state, actually. So it's very well known what this gives you. this gives you exactly, again, this for the upper bound. And yeah, and you can think of it as an ansatz, but in fact, this state is maximally correlated, so we know everything about maximally correlated states. Yeah, so and once again, you have the limit there, so there is a Sego theorem that takes care of the limit. Okay, so it's straightforward. This whole teleportation simulability is a beautiful technique that was already in the original paper by Bennett, and it was heavily exploited and developed by this other blob paper more recently. Okay, so it's kind of cute that Sego theorem appears both in the lower bound and the upper bound, but of course this is kind of expected because yeah, it's the right way to do the limit in this context. Right? Interpolates matrices. Right. Okay, so so we have an exact formula for all this quantum capacities of the bosonic dephasing channel. That's nice. And the proof uses in a critical way this Sego's theorem from asymptotic linear algebra, which is I don't know, I think very beautiful result. And okay, so there's plenty of open problems here because what I've told you so far is all for energy unconstrained capacities. I don't know very much about energy constrained capacities because if you want to do that, you need to control the approximation in the Sego's theorem. And there has been a lot of work done on this, but nothing conclusive as far as I could tell. And the other big problem is what happens if you consider a mildly more realistic model, which is actually even much more realistic because everybody knows that the main source of noise for continuous variable channels in most platforms is loss. So if you want to do any realistic model of quantum communication or anything with quantum memory, it's going to have a lossy channel. Okay, so a quantum limited attenuator if you want. And so we know exactly nothing about the capacities of those guys. So the composition of a bosonic dephasing channel and a lossy channel. We know that they are never degradable unless kind of the composition is trivial. So yeah, that's much more difficult, and it's a very nice problem. Right. Thank you.